Hey guys, what's up? How you doing? Hope all is well. Just wanted to go and do some more of 9.2 right now. So, sorry, 9.3 rather is what we're at right now. 9.3, I'm sorry. And remember, this whole lesson is all about right here, testing a claim. It tests about a population mean. Once again, it's a one sample t-test for mu. All right, so where we were at right now, two-sided tests and confidence intervals. A link between two-sided tests and confidence intervals for a population mean allows us to make a conclusion directly from a confidence interval. All right, so a conclusion directly from a confidence interval. If a 95% confidence interval for mu does not capture the null value, the null value m sub o, we can reject h sub o, which m equals m sub o, in a two-sided test at the alpha equals 0.05 significance level. If a 95% interval for mu captures the null value m sub o, then we should fail to reject h sub o, m equals m sub o, in a two-sided test at the 0.05 significance level. So basically what we're saying is we can look at the confidence interval now and see if it's a two-sided test, see if the null should be rejected and the alternative is convincing evidence for, or the other way around, we'll fail to reject the null. We don't have convincing evidence for the alternative. All right. The same logic applies for other confidence levels, but only for a two-sided test. So let's take a look at an example right here. Okay. At the Hawaii Pineapple Company, the mean weight of pineapples harvested from one large field was 31 ounces last year. Okay, so right here, it says that right here, the mean weight was 31 ounces last year, okay? A different irrigation system was installed in the field after the growing season. Managers wonder if the change will affect the mean weight of future pineapples grown in the field. To find out, they select and weigh a random sample of 50 pineapples from this year's crop. Okay, so right here, they want to, and notice right here, they wonder if the change will affect the mean weight of the future pineapples grown in the field this year. So they said affect it. They didn't say increase it. They didn't say decrease it. Affect. So that sounds like two-sided. So let's take a look here. Part A, state an appropriate pair of hypotheses for a significant test in the setting. Be sure to define the parameter of interest. Okay, so right here. So the appropriate hypothesis right here. So the null right here is going to be that the mean weight is right here 31, because remember at the very right here, it says right here, this is my null right here. It says that the 31 ounces last year, the mean weight of pineapple. That was like basically the kind of stated claim from before, whatever. Okay. Now the alternative is what we're trying to see. Managers wonder right here if the change will affect the mean weight of future. So that's going to be the alternative right there. And it just says change. So our alternative is just going to be mu does not equal 31. And then right here we're going to say where mu equals right here the true mean weight in ounces of all pineapples grown in the field this year. Okay, so it's going to be right here the true mean weight in ounces of all pineapples grown in the field this year. All right, so what we have to do right here is we're going to go and all we're doing is just stating the hypothesis. But in general, when we state the hypothesis, we should mention what the alpha is. Now notice right here, in this case right here, they gave us an alpha in part C. But if we don't give us an alpha, we just use right here, we're going to use, we will use alpha equals 0.05, okay? Because we know in part C that's what they do anyway. So, all right, we're all good right there. Okay, let's look at part B. Part B says check the conditions for performing the test in part A right here. Okay, so just to highlight, just to kind of mention some things that we need to for the conditions right here. We know that there's n value of 50. All right, we already have the null on top, so we're okay with that. And the whole population, the big N, is just going to be right here, all pineapples, all future pineapples, all pineapples grown on the field. Okay, so that's what we're going to transfer over right here. So we know that N equals 50. All right, so right here, and the big N is just going to be all pineapples. I'm just writing that as my little notes here. You don't have to write this. If you already have the question before, you can just, Okay, so let's do it. So we're going to say random. And it looks like right here they select and weigh a random sample of 50 pineapples from this year's crop. So I'm going to say yes. Random sample of N equals 50 pineapples. Okay, 10%. We have right here N equals 50 is going to be less than 0.10 of big N, which is all pineapples from the field. Okay, and then right here, in this case, it's normal large sample. Now, in this case, remember, if it's greater than or equal to 30, or if the population distribution has said that if the population distribution is normally distributed, we're good. In this case, we know that 50 is greater than or equal to 30, so check. All right, we're good right there. So we're good with everything. Okay, and maybe right here I just should have said right here all pineapples from a large field. Okay, because I believe that the problem originally right here said that it's from a large field. All right, so anyway, let's go to part C. Okay, part C says what? A 95% confidence interval for the mean weight of all pineapples grown in the field this year is 31.255 to 32.616. Based on the interval, what conclusion would you make for a test of the hypothesis in part A at the alpha equals 0.05 significance level? All right, so what I'm going to do actually right here is just real quick. I'm just going to copy this over. I'll put it right here so that I can refer to it while I'm doing the problem. Just a little bit here. Let me move this up a little bit. Sorry about that. Okay, good. Okay. So the 95% confidence interval is from 31.255 to 32.616. Now recall that, just to remind you, the null is 31. Alternative is M does not equal 31. So I'm just write that down. Okay. Based on this interval, what conclusion would you make for a test of the hypothesis in part A at the alpha equals 0.05 significance level? So in this case right here, what we're going to say is the 95% confidence interval does not include 31 as a plausible value. So we will reject the null hypothesis right here. Now we have convincing evidence for the alternative hypothesis at the alpha equals 0.05 level, and the reason it's 0.05 is 100 minus 95 is going to be 5, which is 5%, which is 0.05. So we're going to say we have convincing evidence and the alternative is that the true mean weight of all pineapples grown this year. And what is the alternative hypothesis? It's right there. Is not equal to 31. Or is different than 31, you get to say. Ounces. Okay, and that's it, okay? You can say, you don't need to say with alpha equals 0.05, but if you want to, you can. All right, so part D, let's look here. Can we conclude that the different irrigation system caused a change in the mean weight of pineapples produced? Explain your answer. Okay, so right here. So we had a different irrigation system and there was a change, but can we say that it's the irrigation system? This is going all the way back to chapter 4. Remember, there's a couple things that we have to think about this right here for part D. And before I put the answer, I'm just going to kind of map this out. Remember, if you do random sampling from a population, that means that we can go and infer to the population. All right, if it's random sampling from a population, we can then infer to a larger population. Okay, we can say that whatever happens with this sample, we can infer to the entire larger population if it's significant, right? Now, secondly, though, if we go and do random assignment to groups, that's like, if we have like a control and an experimental group, right? So we were comparing two different groups or any kind, it doesn't have to, it could be two experimental groups, whatever. If we actually have a comparative experiment that's random assignment to groups, then we can establish cause and effect. Now, so what they're asking right here, they actually said right here, can we conclude that this different irrigation system caused a change in the mean weight? So we have to see, was there random assignments to groups? Does not look like it. Okay, they're not comparing it to a typical irrigation system at all. So in this case, what we're going to say is because there was not random assignment to groups, then that just means there was no comparative experiment. We cannot establish cause and effect. And therefore, we can't say the irrigation system, can't say the irrigation system caused the change in mean weight. Okay, something about like that. The book's answer, if you look at the book's answer, they went into more detail, but all you have to say is there wasn't random assignment to groups, there was no comparative experiment, so we can't establish cause and effect. Okay, so we can't say the irrigation caused the change in mean weight. All right, so that's it. All right, so let's look. This is the book's answer right here. There's the null. Okay, random 10%. Normal large sample, same thing that we had right here. 95% confidence interval does not include 31 as a plausible value, so we would reject the null. We have convincing evidence that the true mean weight of all pineapples grown this year is not 31. I said different than 31, same thing, okay? And right here is what we just did right here, okay? All right, so that's one example. We'll get to we will get to the last example, which is all about power tomorrow. Have a good day, guys.